But let me thank you for coming on this snowy day. This will reappear when we go through that. This is basically the table of contents of the presentation, and you see it covers a number of things. So that's why it's good to start right away. And also, I want you to bear with me. As you know, I'm a historian, and I come from a wordsmithing culture. So I won't treat you much to formulas, but I will treat you maybe overly to some words. So that's a kind of warning in a way. So I would like to start with the question, how much ethics? Because that is something that our department is focusing on. And that is also something that's not necessarily a center focus, as you will immediately see, for the College of Engineering. So we got recently an email from a full professor in mechanical engineering, and he is also the GPD the graduate program director of mechanical engineering. He was writing, your department requested an approval for the same EST 502 ethics course in the last spring. At that time, I raised a concern that the subject being 3-credit course, I suppose it was not approved because of that. Anyway, I do have a reservation for offering, and note the quotation marks, ethics as a full 3-credit course, although it is a very important matter and everybody should understand it. I mean, how do you balance that, right? Very important, but 3 credit? Nah, it's not that important. Ethics is not an academic subject in engineering, science, technology. As such, the course should be offered as a training course. As we need to take online ethics video, we, professors, online ethics videos, ICOP, or at most, it should be offered as a 1-credit course. Then our GPD responded, the ethics course is integral to our MS program. We teach management of technology and engineering, some to graduate of your programs, mechanical engineering. And Lord knows, we want our managers to have a strong understanding of ethics and to make decisions based on ethical principles. We think the material we cover in the course and the work we ask of the students warrants 3 credits. I hope you will reconsider your comment in this context. And the answer came then a few days later, this time from a full professor in applied math and statistics. And he wrote, I approve EST 519, but disapprove EST 502 for the same reasons that the other colleague had just outlined. In AMS, for example, AMS 500, a 0-credit course, introduces students to the major issue in the ethics of science and research. The course meets for 1 hour for 8 weeks, and each professor is assigned to teach it for 1 week. I agree that an ethics course is not supposed to exceed 1 credit. And then our GPD wrote back, somewhat extensively, as you can see, and he starts very nicely. I'm glad that you and your department are engaged in ethical considerations. I'm not sure that 8 hours are sufficient to cover everything that's needed. However, even for efficient mathematical thinkers. Financial modelers responsible for the 2008 crash might have wanted to consider the ethics of mortgage bundling and reliance on models such as VAR. Mathematics and math-related industries face issues with underrepresentation by particular sets of people, and growing reliance on algorithms, while seemingly providing a level of objectivity as to how decisions are made, also can include a good ration of bias. These are the issues that we consider, he continued, and perhaps it would be not a bad thing if you would approve that, is basically the tenor of the rest of that. The answer came back, hi, based on your explanation, I approve AMS 502. It seems like your program has a lot more topics to be covered in the ethics course than ours. So, straight success, right? But it was a little difficult. And you also see that we are going to face pushback when we focus on ethics. However, I think it is promising that arguments made in favor of it succeeded. So it may be an uphill battle, but it's a winnable thing. Now I would like to introduce what it's meant with automotive ethics. So in April 2019, April this year, I Googled automotive ethics and received over 62 million answers in less than 1 second. The top answer was, and I quote, to perform high-quality repair service at a fair and just price. The first commandment of the Code of Ethics of the American Automotive Service Association. And here you see their ethics code, and the first line of the ethics code is to perform high-quality repair service at a fair and just price. Yesterday I checked again. The top results still pointed to the ASA Code of Ethics for mechanics and automobile dealers. What we may call, and this I think what we could call Automotive Ethics 1.0. Yet Automotive Ethics, Stony Brook University, came also up on the first results page, both yesterday and in April. This was pretty good since we had listed our research initiative only 2 weeks earlier, in March of 2019. These search results show 2 things. The automotive experience of the last century and its associated concerns are still very much with us. Everybody has that in mind in a way. And however, our understanding of automotive ethics as Automotive Ethics 2.0 needs a lot more research and much clarification. And Danielle Byrne and I are working on that. I don't know if you can read the title. Her dissertation is Design and Ethics, the Case of Automated Vehicles Regulation in the US and the EU. And we will say something to this. I will say something to this language in a moment. Now, the difference between Automotive Ethics 1.0 and 2.0 is between an aspirational code of ethics like the 10 Commandments, which human actors should follow, and a pre-programmed algorithmic ethics that automated driving systems will follow. So this is a very important distinction, because the ethics commandments that we are used to, like good repair service, fair and all that, it does not always happen. And the price may be overpriced and all that. So it is an option to behave ethically well. But once an ADS, an automated driving system, is programmed and certain decisions are made in the programming, that system will follow that program. So that has huge consequences, and we will touch upon some of them. Electric vehicles are already here, as we know. Automated vehicles and automated electric vehicles are coming. The latter are no longer human-driven, but steered by artificial intelligence. So these cars that are what we call ADS, vehicles could also be submarines and other such things, they will be programmed in their decision-making. So that's the reason why we want to add the E of ethics to the artificial intelligence of ADS, AI plus E. That's our formula. And here's a footnote on terminology. We distinguish and try to. Sometimes it's not so easy because language guides you along and you use words that you maybe should not use or so. But as you know, when you read the papers or watch, there's you sometimes hear about autonomous vehicles and automated vehicles. And we do not want to mix that up. And the reason for that was nailed by a Nissan engineer when he said a truly autonomous car would be one where you request it to take you to work and it decides to go to the beach instead. So that's, you understand why we want to make that distinction. Now, I want to introduce a little bit our motto and our department motto and what it means. The origin of the DTS motto is the mushroom cloud. This one is actually the plutonium bomb dropped over Nagasaki. And as you can see that it's some handwriting there that says Charles Sweeney, Major Pilot, US Air Force, Boxcar. Boxcar was the airplane that delivered that bomb. And so you Google that, you see the many photos of it. So let me explain the historical background of our motto. Natural science lost its purity in the First and Second World Wars, chemistry in the wake of gas warfare in World War I, physics by building nuclear bombs in World War II. You know that gas was very many, on both sides of the First World War, very many chemists were involved in building gas weapons, and including Nobel Prize winners in chemistry. So that was when basically chemistry lost its innocence, and we know the Second World War. The head administrator of the Manhattan Project was James Bryant Conant. And he was actually an organic chemist and also president of Harvard University. And he was called into service by Vannevar Bush, who was the guy who was overseeing the whole American military effort during the Second World War. And Conant was the one who was in charge of the Manhattan Project. And he concluded after Hiroshima and Nagasaki, that produced this cloud, science is much too important to be left to the scientists. And that's what we took and changed. So today we can say engineering has eclipsed the attraction of physics, but its brand as a purely problem-solving endeavor has darkened. Engineering is now also judged by the problematic consequences of its solutions. For example, biased machine learning, deepfake videos, privacy loss, and Cambridge Analytica distortions have tarnished engineering. Thus, we say engineering has become much too important to be left to the engineers. Now engineering must open up, go beyond technical solutions, and assess social and natural outcomes as well. And what does that mean? What you see here is also a historical reference to when to the 1960s. That's referring to a book from 1965 that Ralph Nader wrote. You may have heard the title, Unsafe at Any Speed. And the photo that's there, and that's the car that he targeted, a Chevrolet Corvair that exploded in flames because it was badly designed. And you know probably about Ralph Nader. He actually funded that museum. And that museum I haven't gone yet through, but I would like to visit it. That museum is in Connecticut, and it's called the American Tort Museum. And you know what tort is? Tort is a legal thing when something goes wrong, and so I mentioned that for a couple of reasons. One is when the self-driving cars that we are talking about make something that can become a court case, that will be, in all probability, a tort case. So the automotive industry is very afraid of what can happen when something bad happens, namely what can happen in terms of the penalties. Again, our focus is binocular. We look at technology and society. We are serious about both technical achievements and non-technical consequences of the algorithms that select or deselect mates, job seekers, or drone targets. Opening up also means engineering students should take a 3-credit ethics course at least. Automotive ethics for ADS means that we consider the employment consequences of self-driving trucks. I mean, this is something we haven't done that much yet here in our department, but there are 3.5 million truck drivers in the US. The total trucking industry employs over 8.7 million people. And 90% of the people involved in trucking, that's 7.8 million, may lose their jobs when self-driving trucks come on the roads. And that is 2.4% of the US population of 327 million. And all transportation and material moving is at risk to the order of 55% job loss. So these things that on the one hand are great accomplishments and achievements have also great consequences. And for a department like ours, technology and society, these societal consequences are relevant. However, I would like to say, when we say it's much too important to be left to the engineers, I also want to make clear that that does not mean that technical expertise should be a secondary qualification. I mean, someone could say, so we want that we are not looking, I mean, that people can invent all sorts of things that have nothing to do with reality and so on and so forth. No, that's not what we want. And here's an example, recent one. The 737 MAX disasters that Boeing was responsible for have proved this point. In 1996, Boeing acquired Brannan-Douglas for $13 billion. After their merger, and I quote from a recent article that's very interesting, Boeing went from being led by engineers to being led by business executives driven by stock performance. Here you have an interesting shift, and I've observed that in Europe also and in other places, that in the last 40, 50 years, that has happened in many companies. Companies that are producers of technical goods or chemical, pharmaceutical, or something like that. All of a sudden, there came a shift, and the top management became were business-educated people, and the chemists in pharmaceutical and the engineers and others were pushed to a secondary rank. And that has consequences, and that one of the consequences, and that's why this article that's mentioned here, the case against Boeing that you can find in the New Yorker, is very interesting, because the second disaster of the 737, there was a young woman in that. And it turned out, somewhat eerily, that she is a relative of Ralph Nader. And so Ralph Nader, who was the one that went in 1965 in his book Unsafe at Any Speed against the Chevrolet company, against the Chevrolet, Ralph Nader was also responsible for something that we study. I mean, Daniel studies the NHTSA. the National Traffic Safety Highway Administration, and their regulation attempts at self-driving cars. And the NHTSA goes back to Ralph Nader's book, Unsafe at Any Speed. So there is a connection, and now the family, Nader and the family that lost that kid and all that, as you can imagine, they have pledged to not let Boeing get away with that. So this is going to go on and will become very, very important, but it has a deep background, as you can see. Now I want to give you a little bit of context. And the context I want to give you is, on the one hand, our growth as humans and our shrinking adaptation time to innovation. And there are, when you look at human history, and some of us study energy history and so on, there are only 4 major global energy transitions in human history. The first was the domestication of fire. That had enormous consequences because you could now move in different parts of the world. You could, winter became a different thing, and on and on. It's a very important thing. And the domestication of fire means that fire could be kept. You did not have to wait for lightning to strike or things like that. And the second was the domestication of plants and animals, what we call the Neolithic Revolution. The third was the domestication of fossil fuels. That's connected to the Industrial Revolution, as you know. And the fourth is the domestication of nuclear power. These 4 transitions, each of them, have increased the carrying power, what is called carrying power of the planet, how many people the planet can sustain. And I don't want to go into the details, but give you only one example. If you have hunters and gatherers, you know these groups are not more than 30 to 50 people, if many. And they need, because they are not creating food, they are taking what they find. And for that matter, the size of humanity on the level of hunting and gathering is limited. And that means the carrying capacity of the Earth is limited. And here are the consequences in terms. There was the highest number of hunters and gatherers that this planet ever had was about 1 million people. That's all, 1 million. And that was around 10,000 BCE. And I took that time because then starts the next revolution. That's the domestication of plants and animals, what we call agriculture, right? That starts about 12,000 years ago. And that gets then eclipsed by the next global energy transition, by the Industrial Revolution. So we can look at the number of people on the planet around 1800. That's when the Industrial Revolution takes off, right? And then we see it is 1 billion people. So 1 billion farmers, from 1 million hunters and gatherers to 1 billion farmers, the carrying capacity, the load capacity of the planet. Around 1950, 2.5 billion industrialists. Currently, we have 7.7 billion in terms of world population, and we estimate that 10 billion people will live in fully industrial world by 2050. And just for the fun of it, I added, it is not inconceivable that this planet could sustain 100 million people, because you see these are levels of magnitude increases each time. If we get, let's say, something like fusion power, which is currently very heavily worked on. And also this is not impossible, because we have moved now basically as humans into living in cities. So cities, compared to what hunters and gatherers, for instance, need, have a very small footprint. And they go vertical. So you can, we have done some of these calculations, it's possible. But is it likely? We don't even manage to steward this planet with 7.7 billion right now. So I mean, it's you can see the magnitude also of the problem. Now, the rub of that is that disruptive change has to be weathered in ever shorter time span. And with disruptive change, I mean when you go from hunting and gathering to farming, when you go from farming to industrial, and when you go from industrial to post-industrial, or what you want to call it. These are big big changes. And when you look at the attached time frame, you see that hunters and gatherers had over 1 million years, which is 90% of human history, to adapt to their lifestyle and kind of go as far as they could. Agriculturalists had 12,000 years, farmers, right? And it was very slow moving because, as you know, I mean, the cities only start then a few thousand years ago. And in the beginning, of course, there were many, the farmers were not really, it was not clear that this was the better lifestyle. So it was a very slow moving change. Industrialists now had 200 years. And the nuclear age dawned only in my lifetime. The first nuclear reactor became critical. Fermi did that in Chicago in 1942. That was the year I was born. So that is, what does that mean? That means that humanity's adaptation window has shrunk by 6 orders of magnitude, from 10 to the power of 6 to less than 10 to 1. Are we prepared for technology-driven change in ever shorter time spans? It's, I think, a fair question, because these changes that are now occurring have been, as we can see, the speed up or the compression of time from 100,000 years to 1,000 years to hundreds of years to decades, that now change is going on, that we are now saying, well, you don't bother to learn too much, you have to learn all your life. So keep learning simply, right? Because it's so much change will come into your lifetime. We don't have not even hundreds of years, which is a short time span, for major changes. And with the automotive ethics, we are talking about some major change and other related things. So the answer is we are not prepared, far from. The Industrial Revolution, and now I give a little bit of somewhat of a hopeful twist to that situation. The Industrial Revolution was a local steam engine affair when it started, but is going global now. I mean, that's also something for our understanding of the time we are living in. That's very important. The Industrial Revolution, when you hear about it, it's kind of school stuff, right? But it's not over. It's really, you could say, beginning now. I mean, it has moved. I mean, it was going on all the time. Yes, it was the initial start was around 1775 or whatever, around that. But nobody saw it. It was a little tiny speck somewhere in the hinterland of England. But now it's going global. And you know what the population sizes of countries like China and India are. So this is now, and the footprint of industrial lifestyles, the industrial lifestyle, is enormous. And that's only now really settling in or becoming, so anyway. However, the fourth industrial revolution, that's something that's also now increasingly talked about, which is called Industry 4.0, is offering some powerful help. It combines human and machine intelligence. You see on this graph here, the fourth is called, it has intelligence, a human brain, and networked connections. It is a situation that promises a much more rapid tackling of problems. So you could say our time has shrunk, but our computing power and the combined computing power and human intelligence can now, that's what I say, hopeful, right? I mean, may be able to solve big problems in much shorter time frames. Intelligent cyber-physical systems, such as robocars and trucks, can herald super safe travel, we will say more about that, and efficient transportation. Now I want to go quickly through some big assumptions and then return to the automotive topic. But these are basically framework assumptions that I want to just rush through. Humanity is building a global techno-scientific civilization at this moment, and I have called it Pangea 2. You know what Pangea is? Pangea means all Earth. Pangea was also a concept that was created when there was a first understanding that the Earth's continents are moving, and that there was once a Pangea 1, that all the continents were together surrounded by a world ocean. And we have now created, I say, Pangea 2 with communication systems, satellites and all that. We don't have to wait another 200 million years until the Earth is one again. That's the argument. Cyber-physical systems, which are the signature feature of Industry 4.0, support Pangea 2. Smart design is the core business of Industry 4.0. Everything, from genetically engineered fish to cars without steering wheels, is design-based. Breakthrough technologies such as AI, biotechnology, especially CRISPR, nanotechnology, fifth-generation wireless, and quantum computing permit design across physical, biological, national, and disciplinary borders. Designing cyber-physical systems across political, natural, and academic boundaries empowers inter- and transdisciplinary team science. We are harnessing team science here in vertically integrated projects. You know some of them. Different political and regulatory cultures will impact the design and release of AI-controlled vehicles. That's something we are looking into actively, especially Daniel. Creating the next disruptive innovation is driving technology entrepreneurs in the US. This dream, I mean the obsession, I want to create the next app or whatever that is disruptive. So disruptive has gotten a very positive turn in that context. Normally the design of disruption promising projects proceeds without much attention to ethical responsibility, social harmony, and global sustainability. Yet AVs and AEVs, the electrical automated car, warrant the inclusion of a strong moral machine, even in predominantly deregulatory environments. That's a hint that we think that we are living here in the United States in a predominantly deregulatory environment. Because AI-driven vehicles are responsible for their potentially harmful and costly driving decisions. And that's why I think that AI plus E enables controlled disruption. So that's an important element, that the Teslas of this world, they are the embodiment of disruption in a way. But we also, with looking at the automotive industry, we are dealing with very old, century-old industries. And these industries, which I will say in the following, these industries are not natural promoters of disruption. However, what the economic pressure to create these self-driving vehicles is so high that they all work on it. But my assumption here is that we can count on the traditional automotive industry to try to get a handle on that disruption that they are also furthering. And that's what I call controlled automotive disruption. The traditional automotive industry is inclined towards controlled disruption. As one of the world's leading economic sectors by revenue, it competes on a global scale and will catch up with pioneering disruptors like Tesla. For self-preservation, their self-preservation and continued leadership, the established automotive industry will pay careful attention to three things: national and international road safety regulations, social and ecological sustainability, as well as the demands of AI plus E. So my forecast is the large-scale introduction of AEVs will disrupt established patterns of transportation and mobility worldwide, yet also save countless lives. And I have some footnote here. I mean, road traffic accidents are the 8th leading cause of death for all age groups. It's a huge burden of death that the traditional traffic has. So they will pay, they will save countless lives. Highly effective automatic safety measures will significantly reduce motor vehicle collisions and curb the pollution caused by fossil fuel vehicles. I give also some details in the footnote that some countries have already outlawed and given the date when that's going to happen, diesel vehicles and so on and so forth. Additional benefits can be expected in the area of raw material procurement. That's an issue that has mainly to do with lithium-ion batteries, which are where the components are mined under the most horrendous conditions. And now to the baby steps that the automotive industry is going to do. BAST is the German regulatory agency. The NHTSA we have mentioned, that's the American, and the SAE is an International Association of Automotive Engineers. And they have classified the levels of automation in cars, and as you can see, the German ones have only 5 levels, but the level that we normally go with is the SAE level, and that has 6, starts with level O and goes up to level 5. One can say the race to increase the levels of vehicle automation is on. One can also say the AEV revolution is underway. But one cannot say the paradigm shift to AI-driven vehicles is all but accomplished. However, that is what Elon Musk said in April 2019. Because Elon Musk, I mean, he's a wonderful engineer, very visionary and all that. No problem with that. But he is also a businessman, and he has to keep the stock of Tesla up. So he talks up what he is doing, and that's his saying. So he said, what I quote here, that next year there will be a fleet of 10,000 robotaxis or so that will be completely driving on their own. And that is bullshit. I mean, that's not going to happen. Consumer Reports and the Industry Coalition Partners for Automated Vehicle Education, with a nice acronym PAVE, immediately declared such claims premature and not backed up by the data. Currently commercially available automated cars are only partially automated. That's level 2. There is currently no commercially available car on the road that goes beyond level 2. So that's, I know that BMW next year will introduce, and they always introduce it with high luxury cars, for an additional, I don't know how many, tens of thousands of euros, you can get then an assistance element in the car that allows the car to drive at the speed of 40 kilometers per hour in a traffic jam. So everybody is slowly moving forward. Then you can turn to the people in your car or read a book or whatever that the car will do. But that is, and that's the way these things move. That's the way the automotive industry moves this thing, little step by little step. I in Berlin had a car a few years ago that was already could park. I mean, this when you have to crunch your neck and park in, right? It realized there was a parking opening, and then it went in. And it was very funny because the steering wheel turned on its own and so on. So these step by little step, that's how this is going. Not all of a sudden we wake up and we have full automation. Now, this is a plea for automotive ethics now, but the right way. The best time to accelerate research into automotive ethics 2.0 is now, ahead of the widespread use of level 3 to 5 vehicles. And here's the reason why. The awareness of ethical problems in engineering and applied sciences tends to rise when applications become ubiquitous. Take facial recognition technology. What was an innovative idea and tempting AI challenge turned into a Black Mirror type issue after it was adopted wholesale by the police in China and elsewhere. We can do better. In order to move from a reactive to a proactive stance, we must investigate the moral hazards of emerging AI technologies before they massively arrive. If we wait until potential risks have become realized, our options and associated timeframes will be severely restricted. Hence, the time to accelerate research into automotive ethics is before ADS are in widespread use. Because sometimes when something new and innovative gets into the world, then or in massive amounts, then you see, and then certain constellations and situations occur that show what can be wrong with that. Most when it's developed in laboratories, it's on test drives, and so on and so forth. It doesn't show. So that's why, and if you keep in mind that our time frames tend to shrink, then there is no time to waste to start looking into that. So how not to do automotive ethics is the next thing. And some of you may know that. This is the famous moral machine experiment that MIT conducted a little while ago. And it's a good example for the mass collaboration that social science can get these days. And here the data are that people from over 233 countries and territories, must be many territories because I know the UN is only 193 nations. So I mean, how to get to 233, I don't know, but that's the number I got from them. And it provided over 40 million decisions. So people that went through that, I mean, you can still go to the website and play that game, over 40 million decisions in 10 languages. So this is a huge data set. And here's the situation that we see here. The automated vehicle, this blue vehicle, has two options because its brakes are out. Kill either one male and two female executives or 3 criminals. These are criminals. I mean, the picture is, these are, they suggest because they have bags with dollar signs on it. And these are 2 females, as you can see, and they are executives because they carry the executive handbag. So this is, if the car goes straight on, it kills the 3 executives. If the car swerves, it kills the 3 criminals. But note also, please, the 3 executives are disregarding a red light. And the 3 criminals cross legally at green light. How should the AI now be programmed? And that was the question where you got the 40 million answers for the whole suite of scenarios. So the people went and in massive amounts answered these questions. So, and I would like to say very strongly that this is the wrong approach. The moral machine of an AV should not take social properties into account. I mean, when we start ethics, when we start talking ethics, we have to make some decisions at some point and have to make some statements of this kind, right? That says yes or no, do this or do that, not this. And here I say the moral machine should not take social properties into account. And there's, of course, a big background in philosophy. I mean, this is an argument that Rawls, an American philosopher, would make, but that would lead us astray now. Social facts like rich or poor, slim or overweight, occupation, religion, gender, and sexual orientation should be off limits in the determination of lethal action. Lethal action that the car will take, right? Yet by doing just that, invoking social properties, the MIT experiment triggered the targeting of supposedly lesser people. Like when you say, well, kill the criminals, right? I mean, in this scenario. By testing people's biases, it laid open global structures and of discrimination and profiling. That was good social science, but invited bad ethics as well. One more thing. If the AV knows that the 3 men who are crossing the street legally at green are criminals, the vehicle's AI must have access to police records and other relevant databases in real time. With 5G, that's not impossible to imagine. As far as I'm concerned, however, responsible AI plus E should not be allowed to make lethal decisions based on police or other surveillance data. Now, a little closer to what automotive ethics does. So there's again, of course, there's always a little bit of a historical background. So Asimov was a science fiction writer that many of you know. And he came up with the first attempts to resolve the tension between values and facts for intelligent robots. And thus he formulated also in 1942 his 3 laws of robotics. First, a robot may not injure a human being or through inaction allow a human being to come to harm. A robot must obey the orders given to it by human beings, except when such orders would conflict with the first law. And third, a robot must protect its own existence as long as such protection does not conflict with the first or second law. So these are the famous 3 laws of Asimov. What Asimov does is he extends humanity's religious and philosophical rules tradition, which includes do no harm, from fellow human beings to robots. This may work as a general guideline. Yet problems with Asimov's laws emerge when we ask, what exactly counts as harm? Does lying, trespassing, or intrusion of a person's privacy constitute harm? What if harm is only likely? Can't any action or inaction result in some kind of harm? And what happens when all available choices are harmful? Should the robot stop dead? To avoid these pitfalls, functional AI plus E has to specify exact thresholds to save robots from debilitating paralysis. I mean, if you apply it to a car, the car would stop. That would be the debilitating paralysis. We have that actually experienced already with Waymo cars, because the Google engineers programmed Waymo cars to take a stop sign by its word. The Waymo stops. Everybody around it makes a rolling stop. Nobody stops. The only car that is stopped forever is the Waymo, because it follows the rules. Recent work on automotive ethics has applied Asimov's laws to AVs. An automated vehicle should not collide with a pedestrian or cyclist. An automated vehicle should not collide with another vehicle except where avoiding such a collision would conflict with the first law. And third, an automated vehicle should not collide with any other object in the environment except where avoiding such a collision would conflict with the first or second law. If you think that true, you will come to the conclusion that in some cases, under some conditions, the automated car has to kill the passenger. And that's it's an interesting consequence. If you are in the market for buying a super safe Mercedes, and you know the car is going to kill you under certain conditions, the term of art philosophers use for strict obligations like those above is deontic. Kantian philosophy is a typical deontic philosophy or moral theory. The problem with deontology is its moral rigor. Deontological rules leave no wiggle room for negotiation or situational adaptation. And the opposite of deontological reasoning is called consequentialism, and utilitarianism, that you know is also an offshoot of that. It argues that any action or inaction that produces a good outcome is morally right. And two authors I quote here use now in their attempts to develop Automotive Ethics 2.0, they use both terms to impart optimal ethical behavior into automotive AI. To achieve this goal, they map both theories onto mathematical programs that control the vehicle's decision making. And now we are coming closer to the end, and I want to give you now just one example of how moral math problems look and what they can have as a consequence. When a computer scientist programs an automotive robot for responsible driving, tricky problems emerge. For example, and I give you that example. A fully automated SAE Level 5 vehicle cannot avoid crashing into one of two cyclists. Yet it can select which one. The one who is wearing a helmet or the other one who is not. What is the responsible choice? Hitting the protected or the unprotected cyclist? The answer seems to be target the person that is more likely to survive. Hence, the carefully programmed car hits the guy with the helmet and not the other who might die. Now, the AV has saved a life, yet also penalized lawful and prudent road behavior. Furthermore, this responsible crash optimization program has now set the stage for more cyclists like him to forego helmets, because doing so has become safer with respect to the optimal targeting choice of the automated car. Writing moral values into the algorithms of automated cars, however, is necessary and unavoidable, but also fraught with uncertainty and unintended consequences. One of the technical theories that engineers, electrical and computer science use to map such decisions into the machinery is called optimal control theory. It's a mathematical method which is directly analogous to consequentialist approaches in philosophy. What it does is it translates the ethical implications of all actions and inactions into cost functions, which in turn allow the software controller to reward desired and penalize undesired actions. So hitting some obstacle has a cost. Hitting a person has a higher cost, and so on and so forth. This method can guide a rocket to its destination, which it does, and give automated vehicles smooth steering and safe braking. It's always calculated, and then calculating the cost of property damage versus personal injury, or the difference between occupant versus pedestrian protection, is in reach of this technology. The problem is neither mathematical nor philosophical, but rather the development of acceptable, socially acceptable cost functions. Here's the joke that they have a real great killer feature in this car, and there was is an example when in 2016 a Daimler Mercedes-Benz manager was quoted saying, "If you know you can save at least one person, at least save that one, save the one in the car. If all you know for sure is that one death can be prevented, then that's your first priority." The media immediately exploded. Car and driver headlined, "Self-driving Mercedes-Benzes will prioritize occupant safety over pedestrians." And there's a lesson here. Morality by math, which is a very nice term that Patrick Lim, who is an author who has written a lot about automotive ethics, one of the first, is not natural. It has to be researched, taught, and explained. The mathematical morality of control algorithms must be made transparent, and understandable. I want to give you now how that is done in actual practice of programmer, a little example. I will explain it and then run it again. The video shows how the collision with two cyclists is prevented by a programming switch from consequentialist to deontic logic. Instead of making the potential collision 1,000,000 times more costly, that's what you can do if you operate with cost functions. You can say hitting a cyclist costs you $1 trillion, or so, a huge thing, but it has mathematical consequences because then everything is out of whack if you make such a big change. So instead of making it more costly than a lane change, for example, the programmer has put a firm constraint on the optimization process illustrated by the purple crossbar. I show you again. This bar is an encoded hard constraint that is a mathematical command instructing the AI, do not pass these cyclists. So here again, green means you can go. Let's go again. And these boxes are the cyclists. You saw the purple crossbar, and that was basically. And I mean, when you go to this link, the film is a little longer. You can see a little bit more. What's also clear, the car, which of course has a 360-degree environmental view, the car knew that on this lane another car was coming, so it could not go out here. So, but I mean, for us, the important thing is how to translate philosophical constructs, in this case ethical ones, into programming language. And that's what this shows. And it's actually, again, not that difficult. The problem is the choices to make. And now, the last, that's a very famous example that many of you know. Yes, the famous so-called runaway trolley problem. It depicts a dilemma situation that asks you to make a life and death decision. 5 will live and 1 will die, or 1 will live and 5 will die, when this guy switches the trolley to another lane. If you take the human at the switch away and automate the trolley, the vehicle's AI is asked to make a lethal decision. Guess what? Nobody will die, the AI programmer says, because my AI will get the Deontic crossbar and stop the trolley before the split in the track. Well, that answer avoids the problem of programming what happens when, excuse my language, shit happens. Original equipment manufacturers and AI engineers are reluctant to engage with thought experiments about lethal dilemmas. They are chasing the science fiction goal of total safety, in which accidents have become a thing of the past. But dilemma-style situations will happen, robots will be hacked, fail-safe systems, I should have said, will fail, and overrides will fail too. Hence, we cannot avoid to investigate and discuss the possibility lethal moral math problems of automated vehicles. And that's the last, which shows the great PowerPoint template that our university gives us, and which I used. But I note that it seems to celebrate change for the sake of change. And what we want to do, Automotive Ethics 2.0 has a goal, and that is super safe automobility and advanced ethics education for engineers. Thank you. We have some time. If you have some time, I have some time. Yes?
So I observed that most of your examples of the need for ethics in engineering had to do with computer science.
Well, it's AI. These cars are driven by an AI, and right. AI is computer science based, no?
Right, but even at the beginning, and so in arguing for ethics for engineers.
Yes. Oh no, if we do that course, I mean, we have to, I mean, it will, I mean, this is basically an application of the ethics problem, right, for this course. But the ethics, requirement of thinking through, I mean, in computer science, I mean, everybody talks about biased data sets, right? So, I mean, one of the very, very big things in that context is actually you have to curate data sets. I mean, that's one of the biggest requirements. And we recently had, there was one of the Shutterstock lectures, the last one, the guy was looking into adversarial attacks, and was very interesting. But I mean, he had a ton of examples. I mean, also the technology of how to do it is that it is of extraordinary importance what the data, what the machine learns from the data. So the data are, and so far, most people are happy to have data. They don't curate the data. I mean, that gets into some kind of work, but also then the curating. That's where you would get the ethics component in, because then you have to get a discussion among the group that's working. So what is potential bias in, or whatever, bias as a general term, of that data set?
And so my examples were to an applied mathematician, so that's why they were.
Right.
That's
right.
why they were chosen that way. If I had come up with examples for the mechanical engineer, they would have been different.
Right.
Okay.
Right.
And
Right. Okay.
You talk to your audience.
Yes. Yes.
So the ethical dilemmas, you presented them as a challenge for automation and development of algorithms and the computer science context. They're also present for human beings, right? I mean, each one of those moral dilemmas could be faced by a human driver, and I was trying to think through this is that maybe there's an advantage of using automated ethics because humans are also so fallible, and I would argue questionable from a moral standpoint.
Yes, I mean, I think you are very right, and I would say I fully agree with the trend of your own feeling. I believe that morality by math will improve ethics. Because, I mean, we always wiggle ourselves out of situations and we make compromises, and also not to mention in the context of cars, we do it by intuition and spontaneous, and sometimes, I mean, there is simply no time for the human to make a decision. So the requirement that everything now has to be on the table before it happens and thought through is of course a very, very strong requirement that will clear our minds, even if and I think for a long time or for some time, we will come to discuss problems where we have no clear-cut solution. But that's much better than the spontaneous and intuitive. And it's of course much better than what the MIT moral machine experiment was suggesting, run over the criminals.
And the idea that you mentioned, the duontic, the idea that the machine is disciplined. So I was a commuter, not with the car, I was usually a passenger in a very hectic scenario, which is California's 101, which is a nightmare traffic situation and still a highway, but people would be, you'd see people shaving, putting makeup on, in the middle of the commute, and then right there would be an accident. 5 minutes later, you'd hear of an accident, and all traffic would stop. And then there's the other idea is that there are edge situations, right? So a car in the city, an automated car in the city is much more hazardous, perhaps, than a car in a highway, where there are other cars and not passengers crossing the street, so you can limit the edge situation. So
I mean, there are many, and I mean, this was just a kind of very big overview of what I gave. I mean, the situations that we will encounter will also request a lot of regulation and policy decisions, because the one question is, do we want to mingle human-driven cars and automated cars? Do you want to, let's say, I mean, the whole situation of cities will be impacted tremendously. Will you make pathways for just automated cars? Because the automated cars among themselves are probably really super safe. Right, but the automated cars in the wild world of us are endangered. And I mean, when you see how people drive, that's the situation. So this has many consequences. So I could see something like a changeover that the high occupancy line on 495 is for human-driven cars, and the other three lines for automated cars, right? But if you bring them together, you have another problem. But it puts for the more ethical concerns, it puts it asks for we don't even know, should we work? So I would caution against the Kantian, the deontic, to make it all strict, because and that's then a question for computer scientists, how to program fuzzy logic that still is understandable. So on the one hand, you cannot program by not making clear what should happen if this happens and so on. But when we drive and cross two yellow lines, we make a quick decision that this is optimal under the given conditions, let's say. But these are interesting programming challenges, how to now write programs, write code that allows for that, because if you always say, follow all the rules, stop signs and yellow and so on and so forth, then that will be creating another kind of hazard and will not be successful. But it's the start. It's...
Yeah. Fuzzy logic.
Yeah. Fuzzy logic exists and could be used. Okay? Yeah? Okay, thank you very much.